In this video, we will show you how to use Mach 3 turn CNC lathe to resurface a Seadoo rotary valve cover. Brought to you by Crankshaft&Co. Thanks for watching.
Hello, in today's video I'm going to talk to you about remachining a Seadoo rotary valve cover. This is a part that is common to all early Rotax engines that had a rotary valve, and that's this piece, which mates up against this cover plate, and there is a gear drive that will spin this plate around, and as you can see, that plate will open and close these ports. Okay, so if you have one of these engines or ever read anything about a Rotax engine with a rotary valve, this is what you're talking about. On my channel and my website, I have many videos and posts about resurfacing these back to original specifications. The reason you want to do that is because when this surface either gets all gouged up or it's worn where it's not flat anymore, this plate can't seal properly, and you will have difficulty starting, or it may not run at all. It depends on how bad it gets. So if you've followed any of my posts or previous videos, you've seen me do these resurfacing operations on a manual lathe, and basically we will do a facing cut on this surface, and then you have to reestablish the right depth by cutting back the land, which is another facing cut, and then there's an O-ring groove that you restore to original dimensions, and then that puts this plate back into the original factory specifications. And what you're going for here is a flatness, also the dimension of the depth of this protrusion. All of that has to fall within a plus or minus 2 thousandths profile. So that's pretty precise, and you do need some good equipment to do that. So with my earlier lathe, I didn't have trouble meeting the tolerance. It is a Harding precision toolroom lathe. However, the surface finish was variable. It was good, but it would vary some, and I had some requests to improve that. So today what we're going to do is we're going to set up the CNC lathe. This is a bigger machine. It's got very few hours on the lathe spindle. I know it's good and tight and true, so we're gonna see what kind of surface finish we can get with that. And obviously once I get this system tooled up, I'll use this from now on. I can just pop the cover plates in the fixture and let the program run, and you know, this will just be another step towards improving my processes here, and hopefully improving the quality of my my products. So I'm going to show you how to do this on a CNC lathe. This is a mill lathe, Shopmaster mill and lathe combined, so the processes are similar. The driving code is Mach 3. And Mach 3 is equipped with, to drive a lathe or a mill. You can drive a plasma cutter, laser engraver, possibly even 3D printers with it. It is practically industry standard, at least for light commercial and home hobbyists. Mach 3 is very used, very widespread. So I'm really going to just use the Seadoo part to demonstrate the Mach 3 on the CNC today. So this will have interest to you if you're doing any kind of CNC work with Mach 3. Really what our focus is today. But in the end, hopefully, we're going to get a good product here and improve my process. So all you Seadoo lovers should, be interested to see how this part turns out. All right, so we're going to get right into the setup of the machine and show you the cut. Thanks for watching. Alright, so here's the machine set up for our facing cut across the face of the RV plate. So I have a good carbide cutter specifically for aluminum. This is cast aluminum. It's not very good material, but that's another factor in all this, trying to get a good surface finish. I can tell you that wrought aluminum machines beautifully, and I don't need to go to these lengths to get a good surface finish. So this really is a worst case. So what we're going to try to do is get our parameters and really our mode of cut to get the best possible results. Now you can go to any machinery's data handbook and you can look up your feeds and speeds for your cut like you would on any lathe, manual or CNC. So for cast aluminum we want to keep a surface speed of around 700 feet per minute. And if you had if you were doing normal turning of aluminum or whatever, that is easily doable by just having a constant spindle RPM that would give you the surface feet per minute that you need at the cutting tip. Okay, that's basic turning. Okay. Now, one reason I think with the manual lathes that some of these surface finishes were viewed as sort of inconsistent was because we have when you're facing over this width of a plate, you've got a wide range in cutting radius. So if you think about it, your surface feet are going to vary widely, the actual surface feet. The surface feet is really just angular velocity times your radius at the tool tip. So if you look at this, we're going from a radius at the end of the cut here of a little over an inch from more than 5.5 inches in diameter out here. So if you just use a manual lathe like I was doing, or you use the normal Mach 3 mode where your spindle speed is constant, you really are never really hitting your optimal surface feet. Only at one point in time will you really be at the optimum. So what we're going to use here is a mode that is available in our CNC system here, which is constant surface speed mode. If you're going to get into this, you're going to have to learn some G-code. G-code is the system of programming that these Mach 3 runs on. So one thing to know about this, the constant surface speed cutting mode can be commanded in your program with the G-code command G96. Okay. I bet 99% of you are using standard, inch per minute feeds with constant spindle RPM, and that is your G94 mode. So we're going to go into G96, and to cancel out of that is G97. So keep those two in mind. That is what we need to add to our program to utilize this mode. And I'm going to show you the program that I've come up with to do this cut, and then we'll actually have the other. After this is really the primary cut, and then the cutting of the land and the O-ring groove. Those are pretty basic. I'll show you those, but because those are occurring over a very narrow radius, range of radii, you really don't need the CSS mode. but we're going to really focus on this large surface here and use CSS mode. Alright, so with that introduction, I'm going to get into the G code right now, and we'll show you how that works. Okay, so what you're looking at here is my G code file for making the facing cut on the rotary valve cover, which is a cast aluminum piece. You want to go look up your surface feet per minute, or that's in English. You would use surface meters per minute, I think, in metric. But for aluminum, cast aluminum, it's as high as 700 surface feet per minute. And when you go into the wizard in Mach3, which is where I started this program, and I recommend that because it's really convenient, but inevitably I always go in and add some of these things, like the fact that we're going to use the constant surface speed. And that line is entered right here. That's how I tell the machine to start out in this mode. Similarly, the first line, when you do a program with a wizard, it's going to put a bunch of standard things in there just to make sure your settings kind of go back to defaults. There's cancellation of tool length and cutter radius compensation. G18, that's important. That tells the machine what is the horizontal plane for swinging arcs, things like that, if you have a curved cut you want to do. And that is the XZ plane when you're in the lathe mode. Well, generally, depending if that's the way you're feeding it. One thing to notice, G94 is put in there by default. That is standard feed in inches per minute, and we won't use G95, which is inches per rotation. So this is the more common, so they put that in for you, but we are going to use that to control the feed of the cutter into and across the part. Alright, so all these positional callouts are what the wizard generates when you tell it where to begin and end the cut, and depth of cut, things like that. So it generates all this very nicely. We have our 700 here. That's all we need. We've told the wizard what our feed rate is for the tool feed, and that is a F command. You see right here, this is a go to this X position, F8, that's 8 inches a minute. That'll be our roughing passes, and then we're going to go down to a slow that down for our finish pass. It's in here somewhere. I can't find it, but I think it's 2 inches a minute for the finish pass. So that's generated pretty easily. I have the coordinate system set up for the part. We're going to put the part in the machine, and then I'm going to switch the video to show you the cutting. All right. So before we start showing you the cut, I want to show you something that is kind of interesting, or at least lets you know you're on the right track here. We go into our normal screen when we start up Mach3 turn, and the CSS LED right here is off, and that tells you you're in standard cutting mode, which is going to be just a regular feed in inches a minute, and the spindle speed is going to stay at what you set. This is S true, that's your spindle speed, and that is that's feedback from the spindle encoder. Okay, so you have to have a machine that has a pickup or encoder on the spindle itself. That'll give you your actual spindle speed here, and that's going to be varying by the machine commands, but it has to know exactly what it is here. That's something you'd use for threading too. That's similar to this, but it's a little different mode. It's not the CSS mode. So what I want to show you is I'm going to load my command file, and I'm going to just kick it off, and it'll read those first few lines. And what it's going to do is it's going to know we want CSS mode. It's going to look at that 700 surface feet per minute. It should adjust the spindle speed and this box to that 700 initially. Then the commands to start the tool feed are going to take over, and based on where the cutting tip is in radius from X0, it is going to then use the 700 surface feet and adjust that spindle RPM. You won't see it here though, you'll see it up here in the S true. So look for this to adjust as that tool is fed into the part. Okay, so I'm going to show you that real quick, and then we'll go to the part. Alright, so what I'm going to do is go into auto mode, load my program, which is the RV facing cut, and you see a nice little toolpath representation, and all these blue lines are just your passes, and we're going from the outside to the inside, not clear to the center of this part, facing it off. This line here lets us know we have loaded the RV facing cut step 1, and we'll go into cycle mode. That actually shows you your program here. So these are the lines you saw before. So I'm going to let it call these first few lines. It'll start the feed, and then just look up here and you'll see the spindle speed speeding up as we go from the OD towards the ID. Alright, so we're going to do a cycle start. Here we go. So the setup positioning is going on right now, and G1 is your first pass. Starts out at 8 inches a minute, and you're going to rev up the chuck to keep the surface feet correct, and then as it backs out for the next pass, it'll do that again, and on and on. Alright. Alright, so we're going to execute the cycle start, and here we go. Alright, I would say that's a very good finish. Alright, let me see if I can zoom in here. Alright, I don't know how well you can see it, but it's very smooth. And I'm sure that's very flat. And next, the program will run to cut the land back the proper distance, and then we'll finish up with the O-ring groove here. Alright, so the flange surface has been cut back the required amount. And that is a good finish too. And I've used the depth mic all around there to make sure that we have the exact standoff distance. Alright, now it would look something like this. Take that all the way around. Now the O-ring groove is the last cut, so we'll use this. It's a parting type cutter to cut a groove. You can see we're down pretty far to the bottom of the groove to begin with, but we will put that groove back in. That's no problem. There's a lot of thickness on these plates. I've never run out of material. Okay, press cycle start. Alright, there you have it. We're completed. We'll take it out of there and we will inspect it, but based on the dimensions that I've input, I've already done the depth measurement with the mic. I showed you that. The O-ring groove isn't as critical. Obviously, the O-ring is elastic and it's made to compress in there, so that looks good.